You have undoubtedly noticed that some things float on top of water, other things sink to the bottom, and some things can float in between. This video will help you understand buoyancy, an effect of fluid on an object. After watching this video, you should be able to explain the origin of buoyant forces and use Archimedes' principle to determine the buoyant force on an object in a fluid. A solid understanding of pressure, force, and density will help you get the most out of this video. Understanding buoyancy is important because buoyancy determines what sinks and what floats. Liquids and gases both generate buoyant forces, so everything in water or in the atmosphere experiences buoyant forces. You are constantly immersed in fluid that exerts a buoyant force on you, and buoyancy is vital for some forms of transportation, such as boats and hot air balloons. Before we tackle something as complex as a fish, let's start by looking at a uniform cylindrical object in the water with top and bottom area A and height h. It has a volume, V object, equal to A times h. With a density ρ object, it has a mass m object of ρ object times V object. On Earth, a force due to gravity of g times m object pulls down on the object. Remember from our discussion of pressure that the forces on the sides will cancel each other out. However, there is a pressure at the top of the cylinder, P top, that pushes down, but there is different pressure at the bottom, P bottom, that is pushing up on the cylinder. The force that results from the pressure is the pressure times the area. Both the top and bottom pressures act over area A. The total force from the fluid is the top to bottom pressure difference times the area. Since we already know how the pressure in a fluid varies with depth, we can substitute this relationship in here, which gives us that the total force from the fluid equals ρf times g times h times a. Note that h times a is the volume of fluid, Vf, that would have occupied the space the cylinder is in. We call Vf the displaced volume of fluid. If the density of the cylindrical object, ρ object, is less than the density of the surrounding fluid, ρf, how does the force from the pressure of the fluid compare to the force from gravity on the object? The force from the pressure is the sum of the force on the top and bottom. And the correct answer is that the force resulting from the pressure is greater than the force due to gravity on an object less dense than the fluid it is immersed in. This net upward force will cause the object to rise until it floats at the top. If the object were denser than the fluid, the total force resulting from the pressure would still be the same, but the net force including the pull of gravity would now be down, and the object would sink. For any shape, not just a cylinder, the important factor is the volume of fluid that the shape displaces. A fluid exerts an upward force, F pressure, on an object immersed in or floating on the fluid. We call this force the buoyant force. The magnitude of the buoyant force equals the weight of the fluid displaced by the object. This is called Archimedes' principle. The mathematical description of Archimedes' principle is that the buoyant force, Fb, is equal to the density of the fluid, ρf, times the volume submerged in fluid, Vf, times the acceleration due to gravity, g. Since density times volume is mass, we can rewrite this as mfg, where mfg represents the weight of the displaced fluid. This is another and often more convenient way of expressing Archimedes' principle. Archimedes' principle doesn't just apply in water. Any fluid, which means liquids or gases, exerts buoyant forces on things that it surrounds. We don't normally notice the buoyant forces from gases because the weight of the gases displaced is so small. The density of the atmosphere is 1.2 kilograms per cubic meter. You displace about 0.06 cubic meters of air, so the buoyant force on you from the entire atmosphere is less than 1 Newton. Buoyant forces from the atmosphere are, however, significant on very low-density objects, such as helium balloons. If it requires a tension in the string to hold a helium balloon down, what can we say about the buoyant force compared to the weight of the balloon? The correct answer is that m balloon g is less than Fb. Since the balloon is being held at rest, the net force acting on the balloon is 0. Therefore, the weight of the balloon must be less than the buoyant force if it requires tension to hold the balloon down. Let's get back to our fish. If the fish is denser than the water, it will sink. If it is less dense than the water, it will float to the surface. Most fish can control their average density by means of a swim bladder, a gas-filled sac. They can compress that sac to sink, expand that sac to rise, or achieve neutral buoyancy and be in equilibrium, manipulating their density to control their depth. But what happens at the surface? A fish might leap out of water, but it does not float all the way out of the water. The fish displaces water, sitting low enough in the water such that the total buoyant force up equals the force pulling down. The buoyant force is equal to the density of the fluid, ρf, times the volume submerged in fluid, Vf, times the acceleration due to gravity, g. The Vf term only refers to the volume submerged or displaced, which may not be the whole volume of the fish or object. If the object can float, equilibrium is reached when it has displaced enough liquid to float. Let's look at another object, such as a boat. The hull of the boat makes a hollow shell. The material making the boat's hull may be denser than the water, but its shape allows the boat to displace more liquid than the volume of the matter that makes up the boat on its own. If the boat were solid, or the material of the boat compacted, it would sink. But a boat's shape lets it displace enough liquid to float. Okay, let's recap what we learned about buoyancy. We set out to explain the origin of buoyant forces and used Archimedes' principle to determine the buoyant force on an object in a fluid. Mathematically, Fb is equal to mf times g, which is the weight of the displaced fluid. The density of an object, compared to the fluid it is immersed in, determines if it floats to the top, stays stable, or sinks to the bottom.